Ellipses are another conic section that, like parabolas, can be described using purely geometric means. And then we can translate that information into points in the plane and use that to say things about the ellipse and describe it using equations. Now, the geometric definition of an ellipse uses a focus, or rather two foci, plural of focus. Whereas a parabola used a focus and a line, which we call the directrix, an ellipse involves two focuses. So given points F and F prime called foci, the ellipse with foci F and F prime and semi-major axis. We'll come back to explain this word later. And semi-major axis A is the set of all points in the plane where the sum of the distances to F and F prime is 2a. So the picture looks like this. We take a couple of points, F and F prime, and then we choose some number, some positive number, and we look at all of the points in the plane where the sum of the distances to F and F prime are equal. And that produces a shape that looks like this. It produces what is commonly described as an oval. An ellipse is the technical term here. So the point is that every point on this shape has the property that if you take the sum of the distances to F and to F prime, the sum of those distances is always 2a. So in order to describe this in terms of points on a plane, we'll set up our foci so that they lie on one of our axes and centered around the origin. The center of an ellipse is how we describe the point that is halfway in between F and F prime, the midpoint of the segment containing them. So we'll have a center here, which we will refer to as we look at the equations of the ellipse. All right, so to describe an ellipse in the Cartesian plane, let's let F be the point 0, C, and F prime be the point 0, negative C for some point C greater than or equal to 0. So we're going to look at ellipses whose center is at the origin and whose foci are on either side on the x-axis for now. The analysis we do here is always going to help us to understand ellipses that are oriented the other way, are sort of oriented vertically. Now we will choose some number a, and we want this number a to be greater than c. Now the reason for that is that we want our ellipse to actually have the shape that we want. Notice that we're going to be looking for all the points where the sum of the distances to the two foci here is equal to 2 times A. Now, if A is less than C, then there is no point in the plane that does it. If you choose some point between them, like say the origin, then the sum of the distances to the two foci will be exactly 2c, and that's the shortest that you can get. The shortest sum of distances to the 2 points is 2c, and therefore if we want the sum of the distances to those 2 points to be less than that, then we won't have anything. It'll be impossible. And then on the other hand, if we want the sum of the distances to the 2 points to be exactly equal to 2c, so if A were actually equal to c, then we wouldn't get an ellipse, we would get just a line. We would just get or line segment rather, the line segment going between these two foci. So in order for us to actually get the shape that we want out of this, we need our parameter A to be greater than C. And that is going to give us a collection of points where the sum of the distances to the 2 points 0, c and 0, c is equal to 2a. So if I take some point here, x1, y1, what we have, the property that defines this is that the point x1, y1 is on the ellipse if and only if the distance from x1, y1 to the point 0, c plus the distance from x1, y1 to the point 0, c is equal to 2a. And we're going to be able to take this equation and to rearrange it in order to determine the equation here. Now, it turns out that's going to take a little bit more work than it did with the parabola, so we're going to do that on the next page. But I want to set up a little bit more of our setup so far before we do that. The first thing I want to look at is this point up here and this point down here, the y-intercepts of this ellipse. Now, this point I'm going to call 0, b and 0, b. And what we have is that each of these two red line segments have length a. And that's because everything's symmetric here. The ellipse that we've drawn is symmetric about the y-axis. And therefore, if the distance from 0, b to the two foci has to have a total distance of 2a, then that means that its distance to either one of them has to just be exactly a. Furthermore, we have that the distance from the origin to either the two foci is c, and that means that we can get a relationship between the numbers a, b, and c based on the fact that we are forming a right triangle here at the origin. And so when we set things up this way, we have that b squared plus c squared is equal to a squared. And we can rearrange this however we want. We can solve for any one of these variables. So that's one thing I want to point out, is that the two sort of extreme points on the ellipse going vertically can be determined by the numbers a and c once we pick those. We can also determine what these points over here on the x-axis are. And in fact, as it turns out, they're going to be the points a, 0 and negative a, 0. And let's see why that is. We have that the distance from the point A0 to the point 0C is equal to a minus c. That's this distance in here. And then we have that the distance from the point a comma 0 to the point 0 comma negative c is a plus c. You've got the distance of c to the left and the distance of a to the right. And if you take a plus c and add it to a minus c, you get, of course, 2a. So that tells us that the points a comma 0 and negative a comma 0 are on the ellipse as well. So we have the following 4 points that we know are on the ellipse. And we've got names for these also. The points a comma 0 and negative a comma 0 are the endpoints of the major axis of the ellipse. The major axis of the ellipse is the longest segment that you can draw going through the center of the ellipse and to opposite sides of it. And the points 0 comma b and 0 comma negative b are the endpoints of the minor axis of the ellipse. The minor axis of the ellipse is the shortest distance across the ellipse that you can get. And so determining the value of these points, or the locations of these points, is usually the key to understanding the graph of an ellipse. Now, I just noticed that I made a mistake here with the notation, which is going to cause us problems if we don't correct it. Sorry about that. The foci, the way I have it drawn, should be c comma 0, negative c comma 0, because I sketched my ellipse out with the major axis being horizontal, and therefore the foci also lie on that axis. Sorry about the confusion there. With that corrected, and let's correct this condition here. We want the distance to c comma 0 and negative c comma 0. Let's work out what the equation is that describes the relationship or describes when a point lies on an ellipse. So let's take this equation, and for the sake of notation, I'm going to drop the subscript 1s from these x's and y's, and so this equation will describe whenever a point x comma y lies on the ellipse that we described on the previous page. So we have the distance formula, which tells us that the distance from xy to c0 is x minus c squared plus y squared, and the distance from xy to negative c0 is x plus c squared plus y squared, with square roots over both of those. And we want those two distances to add up to equal 2a. Now we've got an equation here that we want to simplify that involves a couple of square roots. The way that we're going to do that is eliminate the square root expressions one at a time. So we're going to subtract the square root of x plus c squared plus y squared from both sides of this equation in order to get the square root of x minus c squared plus y squared plus the square root, equals, that was the whole point, 2a minus the square root of x plus c squared plus y squared. Now let's go ahead and square both sides of this equation. On the left, that's exactly going to cancel out the square root expression that we had. On the right, things are more complicated because we're taking the square of an expression with two terms, which means that we actually have to expand it all out. So when we do that, we'll get the square of the first term, which is 4a squared, then minus 2 times 2a times the square root of x plus c squared plus y squared, and then plus the square of the last term, and that will cancel out the square root, and so we'll be left with x plus c squared plus y squared. So we managed to eliminate all of the, or one of the square roots. We still have one left. So what I want to do now is to bring the square root expression that I have over to the left-hand side of the equation, everything else to the right. So if we move this expression over to the left, we get 4a times the square root of x plus c squared plus y squared equals, and then on the right we still have 4a squared plus x plus c squared plus y squared, but then minus all the terms that we had before on the left. So minus x minus c squared and minus y squared. Now before we go on any further, we do want to cancel out things that we can. Notice that we've got a y squared and a negative y squared here. And so we're left with 4a times the square root of x plus c squared plus y squared is equal to 4a squared plus, now expanding out x plus c squared gives us x squared plus 2xc plus c squared, and then minus x minus c squared gives us x squared plus 2xc minus c squared after we distribute that negative in front through. And again, we have some cancellation. The x squared and the negative x squared cancel, the c squared and the negative c squared cancel, and so we're left with 4a times the square root of x plus c squared plus y squared equals 4a squared plus 4xc. Now from here, in order to simplify things a little bit, we'll go ahead and divide both sides, divide every term by 4 to get a times the square root of x plus c squared plus y squared equals a squared plus xc. Now we can square both sides again in order to eliminate the last square root expression. So on the left, we'll square the a, we'll get a squared, and then that'll be multiplied by x plus c squared plus y squared, because the squared on the outside and the square root will cancel. And then on the right, we'll have to expand this out. A squared squared is a to the 4th, and then we'll have plus 2a squared c x, and then plus c squared x squared. So at this step, part 1 is complete. We wanted to get rid of the square roots, and we did. Let's copy what we've got so far and simplify it further. All right, so expanding things out on the left, we have a squared times x squared plus 2cx plus c squared plus y squared. And on the right, we have a to the 4th plus 2a squared cx plus c squared x squared. Distributing the a squared through on the left gives us a squared x squared plus 2a squared cx plus a squared c squared plus a squared y squared. That all equals a to the 4th plus 2a squared cx plus c squared x squared. And now we actually have a decent amount of cancellation and simplification we can do. In particular, notice that this most complex term on either side, 2a squared cx, is in fact exactly the same on both sides, so we can just subtract it from both sides, which cancels those terms out entirely. What we have left is an equation that involves some x squared terms and some y squared terms. And what we are going to do is to gather all of the variable terms up on the left side of the equation and put all the constant terms on the right side of the equation. So we'll subtract c squared x squared from both sides, and we'll subtract a squared c squared from both sides. When we do all that, we'll be left with a squared x squared minus c squared x squared plus a squared y squared is equal to a to the fourth minus a squared c squared. Now, from here, we can notice that on both the left and the right, we can do some factoring of common factors. The first two terms on the left involve an x squared, so we can write this as a squared minus c squared times x squared. On the right, two of the terms involve an a squared, so we can factor that out and get, again, a squared minus c squared. Remember that we had that c squared plus b squared is equal to a squared, which means in particular that a squared minus c squared is equal to b squared, where b was showed where the endpoints of the minor axis were. Thus, we can simplify our expression to be b squared x squared plus a squared y squared equals a squared b squared. Now this is an equation for an ellipse. All of the ones have been, but we're still not at the point that we like. What we would like is an equation where we could just read off a and b directly. And in particular, we'd like an equation where each of a and b only appear once. The way we accomplish this is we divide everything in sight by a squared times b squared. When we do that, we are left with x squared over a squared plus y squared over b squared equals 1. And this is the standard equation for an ellipse. So this is the equation of an ellipse centered at the origin with vertices at the points A0, 0A, A0, negative A0, sorry, that was negative A0, 0B, and 0, negative B. Notice that we can read off from the graph from the equation rather, which of the numbers involved correspond to the horizontal endpoints of the ellipse by looking at which numbers are in the denominator of the x squared term. The x squared term goes over a squared, and a squared determines where the leftmost and rightmost points of the ellipse are. The b squared is under the y squared. That tells us how far up and down the ellipse goes. This is our basic equation of the ellipse. And what's interesting about this whole process is that if you set it up the other way, where the foci are arranged vertically, where you still center the ellipse at the origin, center the foci vertically, and you have a sort of vertically oriented ellipse, you get the same equation. The only thing is that the a squared and the b squared are flipped, because we said at the beginning of the process that we wanted a to be the longest distance and b to be the shorter shorter one across the ellipse, or to determine those numbers. So we have this equation which determines the ellipse. Let's go ahead and summarize this, as we did for the parabolas. So the equation of an ellipse centered at the origin. So with semi-major axis A and semi-minor axis B. So we are going to have two different pictures here. So if we're oriented horizontally, then the equation is x squared over a squared plus y squared over b squared equals 1. And then the foci are at the points c, 0 and negative c, 0, where c squared is equal to a squared minus b squared. And so this picture is the one that we had before, where we've got the foci at c, 0, negative c, 0. We have our ellipse, with vertices at a0, negative a0, 0b, and 0, negative b. And then if we're oriented vertically, we have a similar setup. The equation now is x squared over b squared plus y squared over a squared, because now when we have a vertical ellipse, the denominator of the y term in the equation is the larger one. And in this case, the foci are going to be at the points 0, c and negative c, 0, again, where c squared is equal to a squared minus b squared. So this picture looks like this. We have 0, c here, 0, negative c down here. We have a vertically oriented ellipse with vertices at negative a, 0, a, 0. Oh, sorry, got those backwards again. Sorry. 0, a, 0, negative a for the major axis, and then b, 0 and negative b, 0 for the minor axis. So let's see how we can use these forms of the equations to sketch an ellipse, or to find the equation of an ellipse whose graph is given to us. So let's sketch the graph of the ellipse uh, 16x squared plus 12y squared equals 144. Now, it's not obvious that this is the equation of an ellipse. We'll see in a little bit how we can look at this and, in fact, tell that it is the equation of an ellipse. But what we want to do in order to get this into the same form that we had before is we want to get a 1 on the right-hand side of the equation. We want to get the x squared and y squared terms on the left, x squared over some number, y squared over some number, add them up, and that equals 1. So the first thing that we do is we divide both sides by 144. And when we do that, we get that x squared over 9 plus y squared over 12 is equal to 1. So from here, we can tell a few things. First of all, we can look at these two numbers and determine whether our ellipse is oriented horizontally or vertically. In this case, the larger denominator appears underneath the y squared. This tells us that our ellipse is oriented vertically. Now, for a vertically oriented ellipse, our formula looks like x squared over b squared plus y squared over a squared equals 1. So that tells us that for us, a squared is equal to 12 and b squared is equal to 9. Now, a and b are always positive in this setup. So that means that a is going to be the square root of 12, which we can simplify to 2 times the square root of 3. And to say that b squared equals 9 means that b is equal to 3. We have that we can determine the vertices of the ellipse. So this means that the endpoints of the semi-major axis, of the major axis, has the endpoints, because we're aligned vertically, we're going to have the endpoints 0, 2 square root of 3 and 0, negative 2 square root of 3. So that's where the two endpoints vertically are going to go, because those came from the 12, which was the denominator of the y squared. And then the minor axis has endpoints of 3, 0 and negative 3, 0. That's because the 3 came from the 9 as the square root of the 9, which was under the x squared, and so those are going to be on the x-axis. So 3, 0, negative 3, 0. This is generally enough to sketch the graph of our ellipse. We know that the 4 points that we've sketched out here, the 4 vertices of the ellipse, are going to be the extreme points of the ellipse, horizontally and vertically. We can go further, though. The problem might also ask us what the foci are for this ellipse. So for the foci, we need to determine our number c. We use the relation c squared is equal to a squared minus b squared. Now a squared we can read from the equation. A squared is equal to 12. B squared we can also read from our equation. B squared is equal to 9. So that tells us that c squared is equal to 3. So c is equal to plus or minus the square root of 3. We can always take c to be the positive one. So in fact, this tells us that the foci of this ellipse are at 0, square root of 3 and at 0, negative square root of 3. Furthermore, because we have that a is 2 times the square root of 3, one of the things this tells us is that if you take any point on this ellipse and look at the distance to the point 0, square root of 3 and the distance to the point 0, negative square root of 3, the sum of these distances no matter what point you take on the ellipse is equal to 2 times a, which is going to be 4 times the square root of 3. And so this tells us how to sketch the graph and find the foci of an ellipse given an equation in this form. We can go the other way as well. We can say something like, find the equation of an ellipse centered at the origin with vertices at 5, 0 and at 0, -7. We can sketch out the situation here. We've got the point 5, 0 and the point 0, -7, which we're told are vertices of the ellipse. We're also told that the ellipse is centered around the has a center at the origin, and the ellipse is is symmetric around its center. And so if the point 5, 0 is on the ellipse, then the point -5, 0 is on the ellipse. Since the point 0, -7 is on the ellipse, the point 0, 7 is on the ellipse as well. So we know that the equation of this ellipse is going to be of the form x squared over something squared plus y squared over something squared equals 1. Now, in order to get what's going on here, this is always going to be the square of, well, it's the square of half the horizontal distance across the ellipse. That is the square of the major or minor. In this case, it's the semi-minor axis because the ellipse is shorter horizontally than it is vertically. So this distance right here from the center out to this point, this is called the semi-minor axis because it's half of the shortest distance across the ellipse. And then if we go from the origin up to the furthest point away, this is the semi-major axis. Now, in this case, we can see that the semi-minor axis of this ellipse is 5, the semi-major axis of this ellipse is 7, and therefore, that tells us that the denominator of the x term in the equation is going to be 5 squared. And the denominator under the y is going to be 7 squared. These numbers are always determined by how big the ellipse is in the horizontal direction for the x and the vertical direction for the y. Things match up in the normal way here. X goes with horizontal, y goes with vertical. And so our answer, our final answer to this question, would be x squared over 25 plus y squared over 49 equals 1. We can also find the equations of an ellipse given their foci and some other information. So let's find the equation of an ellipse with foci 0, 3 and I wanted to go 3, 0 on this. 3, 0 and -3, 0 and vertices at 0, 0, 4 and 0, -4. So again, sketching things out, we have a focus at 3, 0, we have a focus at -3, 0, and we have vertices here at 0, 4, and at 0, -4. So because the vertices are arranged horizontally, they're to the left and right of the origin, we know that we're looking for an equation of the form x squared over a squared plus y squared over b squared equals 1, where a is the larger of the two numbers. And we're given that this distance from the semi-major axis is 4, and that's going to be b. Furthermore, we're told that the distance from the origin out to a focus is 3, and that's c here. So we have that a squared is equal to b squared plus c squared. That's the basic relationship between a, b, and c here. Now, we have in this problem that b is equal to 4 and c is equal to 3, which tells us that a squared is equal to 25, because that's 4 squared plus 3 squared, and therefore a is equal to 5. So that tells us a number of things. First of all, it tells us that our vertices out here are at -5, 0 and at 5, 0. We can sketch out the ellipse if we want. And it tells us that the equation of the ellipse is x squared over 25 plus y squared over 16, because b is 4 in this problem, equals 1. Now, let's take this ellipse with this equation and consider what happens if we want to try to solve for one of the variables. So we have x squared over 25 plus y squared over 16 equals 1, which gives us an ellipse like we just had sketched. Approximately like this, going out to 5, -5, up to 4, and -4. So that's 5, 0, -5, 0, 0, 4, 0, -4. Now, this shape, this curve, doesn't pass the vertical line test or the horizontal line test. What that means is that we're not going to be able to solve for either x or y. This is one thing that's different about the ellipse as opposed to the parabola. With the parabola, we could always solve for either x or y, get x as a function of y or y as a function of x. We can't do that with the ellipse. So we can't describe the whole ellipse as a function of a variable, but we can describe half of the ellipse as a function of the variable. And we can describe either the top half, the bottom half, the right half, or the left half. So, to find an equation for the top half of the ellipse, pardon me, what we're going to do is we're going to solve for y and then take the positive square root. Let's see how that goes. If we've got x squared over 25 plus y squared over 16 equals 1, and we try solving for y, then we get y squared over 16 is equal to 1 minus x squared over 25, just by subtracting x squared over 25 from both sides. Now we'll multiply both sides by 16, and we'll get y squared is equal to 16 minus 16x squared over 25. And then we want to take the square root of both sides, but whenever we introduce the square root like this, we actually get y is equal to plus or minus the square root of 16 minus 16x squared over 25. All right, let me rewrite that a little bit nicer. 16 over 25 times x squared. So this means that y could be one of two numbers based on the value of x that we look at. And of course, this is what we expect. If I choose a particular value of x here, then there are two different values of y's that give me a point on the graph. So if I want an equation that describes the top half of the graph, I take the positive form of this. So that gives the top half. The negative form gives me the bottom half. So in this problem, we were looking for the top half of the ellipse. So the result would be y equals the square root, the positive square root of 16 minus 16 over 25 x squared. And that is going to give us exactly the green curve on the graph above, which is the top half ellipse of this, top half of this ellipse. If we wanted the bottom half of the ellipse, then we would go through the same process, but we'd solve for the negative, or we would take the negative square root. So if we take y equals negative the square root of 16 minus 16 over 25 x squared, this gives us the bottom half. In order to get the right or left halves, we solve for x instead. So if we solve for x, then what we wind up getting is x equals the square plus or minus the square root of 25 minus 25 over 16 y squared. And again, the plus or the minus correspond to different half ellipses here. The plus corresponds to the right half of the ellipse, the part of the ellipse that sits on the positive x region of the plane, and the negative corresponds to the left half of the ellipse. So going through this process, we can get descriptions of the top half, bottom half, right half, or left half of the ellipse simply by solving for one of the variables and then making a choice as to which version we want to choose, either the plus or the minus square root expressions. All right, well, now we can talk about ellipses that aren't necessarily centered at the origin. So we'll do this similarly to how we worked with parabolas, in that we're going to take a transformation. So if I have an ellipse centered at the origin with its semi-major axes and so forth, and I'm going to draw it arranged, oriented horizontally, but the principles that we have here will apply to the vertical case as well. Let's see, negative c comma 0 and c comma 0 for the foci. But I also want to explicitly mention the center here. This ellipse has the equation x squared over a squared plus y squared over b squared equals 1. However, if we were to translate this somewhere else and say copy down the same ellipse but shifted now. So that the center is now at the point h comma k. Let's see what we would get. First of all, we can see that the foci would shift up here, and we'd get the numbers h plus c0 and h minus c0 as the foci of the new ellipse. Instead of a comma 0, it would be a plus h comma 0, and negative a plus h, I'm sorry, not comma 0, but comma k, importantly. And the points 0 comma b would go to h comma b plus k. Point 0 comma negative b would go to h comma negative b plus k. And all these points go with the shifted version of the parabola. And we know that shifting ellipse. We know that shifting an equation is done by replacing x with x minus h squared and y with y minus k squared. So this is the equation, x minus h squared over a squared plus y minus k squared over b squared equals 1. This is the equation of an ellipse that is centered somewhere other than at the origin. So let's write down what the two cases are that we have, and I'm actually going to copy this figure here and use it on the next page where we summarize what's going on. I'm going to do that. Actually, I'm going to put it over here. Oh, and it looks like I did that. Yeah. Okay, so we have that for the horizontal ellipse. The horizontal ellipse with equation x minus h squared over a squared plus y minus k squared over b squared equals 1 has a center at the point hk, has vertices at the points that we sketched out here, negative a plus h comma k, a plus h comma k, h comma b plus k, and h comma negative b plus k. And the foci are going to be at h minus c comma 0 comma k. Oh, I made that and h plus c comma k. All right, the y coordinates of the two foci should be the same as the y coordinate of the center in this diagram. And then for the vertical case, things are similar. The center at the point h comma k. And then now our ellipse is oriented vertically. So our foci are going to be at h comma k plus c and h comma k minus c. Our vertices are going to be at h comma a plus k, h comma negative a plus k, then b plus h comma k, and negative b plus h comma k. And so the equation of this will now be x minus h squared over b squared plus y minus k squared over a squared equals 1. The center, again, at h comma k, the vertices at negative b plus h comma k, b plus h comma k, h comma b plus k, and h comma negative b plus k. And the foci are at h minus c comma k and h plus c comma k. And so if we're given an equation that's in this form, one of the two forms we have up here, then we can graph the ellipse. And if we're given an ellipse in this form, we can determine the equation. The thing that we have to work a little hard at, which we'll see in a second, is what if we're given the equation of ellipse that isn't in this form? But we'll handle that in a second. Let's first work with these ones. So let's graph the ellipse given by x minus 1 squared over 49 plus y plus 3 squared over 16 equals 1, and find its foci. So the way that I like to do this is the following. First, we want to identify which way our ellipse is oriented. From here, we can see that the ellipse is going to be oriented horizontally because the x term has the greater denominator. So we're horizontal, which means that we can figure out what our values of a and b are. And a is going to be the square root of the larger denominator, b is the square root of the smaller denominator. So in this case, a is 7 and b is 4. Furthermore, we're told that the center we can read off from the equation. With the x, we have x minus 1, so that means that the x coordinate of the center is 1. The y term has y plus 3, so that means that the y coordinate of the center is negative 3. So this is enough to go ahead and start graphing. So we're told that the center is at 1 comma negative 3. Oh, and I realize I need need some more space here, so I'm going to shift this up. And then this number, the number that we get from the bottom of the x term, tells us how far we move horizontally. So we will move from the center, we will move horizontally 7 units to get our vertices, 7 units to the left and to the right. So moving 7 units to the right will give us the point 8 comma negative 3. That's going to be one of our vertices. Moving 7 units to the left will give us the point negative 6 comma 3. That's another one of our vertices. And I got that because 7 was the square root of the number underneath the x term. And then we're going to move vertically 4 units in order to get to the vertices above and below the center, and that's because the square root of the number underneath the y term is 4. So we get -1, we get 1 comma 1 and 1 comma -7 as our two vertices there. That gives us enough information to sketch out the graph of this ellipse, and this one's pretty big. Now for the foci, of course we always use the fact that c squared is equal to a squared minus b squared. A squared is always just the largest denominator of the two terms, so that's going to be 49. And b squared is the smaller denominator under the two terms, which is 16. 49 minus 16 is going to be 33, so c is going to be the square root of 33. So that means that our two foci are going to be, not sure exactly where they are. We can put this into a calculator to get an approximation if we really needed to. But we do know that they're going to be going left and right because we have a horizontally oriented ellipse. And so the y coordinates of each of these are going to be -3, the same as the center. And the x coordinates are going to be what we get by taking the center and adding and subtracting our value of c in order to get 1 plus the square root of 33 and 1 minus the square root of 33 as our two foci. So this is how we can graph an ellipse given its equation in the form that we're looking for. On the other hand, we might say something like find the equation of an ellipse with vertices at 3 comma -2, 3 comma 8, 4 comma 3, and 2 comma 3. So something like this, again, if we sketch it out, that'll help us a lot. So we have vertices at 3 comma -2, 3 comma 8. Oh, sorry, don't know where that came from. 3 comma 8, 3 comma -2, and we have 4 comma 3, and we have 2 comma 3. Now, one thing that we do need to figure out in these cases is what the center is. And if you have two of the vertices, then the center is always the point that's halfway in between them, the midpoint of the segment connecting them. So in this case, we can see if we take the two vertices, for instance, 2 comma 3 and 4 comma 3, we can see that the midpoint of those two is 3 comma 3. So in this case, we know that the center is 3 comma 3. And we can see that from that center, we can see that our vertical distance to the ellipse, to the actual point on the ellipse, is 5. Because if we just take distance from 3, 3 up to 3, 8, we see that's a distance of 5, the difference in the y values. And we have that the horizontal distance to the ellipse is 1, because from the 0.33 to the 0.43 is a distance of 1. And that's all we need in order to write down the equation of the ellipse. So it's always going to be x minus h squared over a number plus y minus k squared divided by a number equals 1. Now, the number underneath the x is always the square of the horizontal distance to the ellipse from the center. So, in our case, the horizontal distance from the center to the ellipse is 1. So that's going to be 1 squared in the denominator here. And over here, it's going to be the same, but for the vertical distance. So we have that the vertical distance from the center out to some point on the ellipse is 5, and therefore the denominator of the y term is going to be 5 squared. And then we put the coordinates of the center in the numerators here, x minus 3, y minus 3, because the center is at 3, 3. And so we have our answer. The equation is x minus 3 squared over 1 plus y minus 3 squared over 25 equals 1. Now, sometimes ellipses, the equations of ellipses are not written in this nice standard form where we can immediately read off the semi-major and semi-minor axes and the center. Sometimes things are expanded out. So for example, let's take this same equation, but I want to expand it all out into a form that we see the equations of ellipses in somewhat more often. So let's take this x minus 3 squared over 1 plus y minus 3 squared over 25 equals 1. And I just want to basically expand all this out. And I'm going to start by multiplying both sides by 25 in order to get rid of that denominator under the y's. So I get 25 times x minus 3 squared plus y minus 3 squared, because the 25's cancel, equal 25. Now let's expand things out. Now we get 25 times x squared minus 6x plus 9 plus y squared minus 6x plus 9 equals 25. If we expand further, we get 25x squared minus 150x plus 225 plus y squared minus 6x, 6y, that should be, minus 6y plus 9 equals 25. And now if we arrange it in the most common way, which is to have all of the variables on the left in descending order and then all the constants on the right, we might rearrange this to look like 25x squared plus y squared minus 150x minus 6y equals negative 209. And when written like this, it certainly doesn't look very much like the equations that we had before. It's not clear at this point whether this is even the equation of an ellipse, and if it is, we can't immediately read much information off of it. In fact, the fact that we still have this 25 sitting in front of the x squared is sort of an accident, because the equation we started with had a 1 in one of the denominators. If that wasn't the case, then we wouldn't even see that 25 surviving in this equation. So the question that we have to answer is, when will an equation describe an ellipse? And when it does, how do we actually figure out what the properties of it are? What's its center? What are its axes? Which way is it oriented? Etc. So let's look at that. So the fact is that an equation, or a polynomial equation, of the form ax squared plus by squared plus cx plus dy equals e, where a, b, c, d, e are real numbers, and a and b are greater than 0, describes an ellipse. Or is degenerate, meaning it describes a segment or has no solution. We don't need to worry about those, the last conditions over here. If you choose your numbers in just the right way, it's possible that you can get an equation that doesn't have a solution, for instance. But the point is that an ellipse is described by a degree 2 polynomial equation where the coefficients of the x squared and the y squared are both positive. Now, a parabola is one like this, but where one of a and b are 0. A parabola is described when you've got an equation that looks like this, but either a is 0 or b is 0, and that gives you parabolas that are either oriented to the left or the right. If one of these numbers, if one of a and b is negative, then in fact you get a hyperbola, which is another kind of conic sections. But if a and b are both positive, then what we have is an ellipse. So, for example, the equation (9x squared plus 2y squared plus 36x minus 12y minus 18 equals 0 describes an ellipse. So you'll notice that this is arranged a little bit differently. Instead of my constant term being over on the right-hand side of the equation, it's on the left. That doesn't make a whole lot of difference because we can just move it around back and forth. What you're looking for are the x squared and y squared terms both being on the same side with positive coefficients. In this case, the coefficient of x squared is 9, the coefficient of y squared is 2, and therefore that means that this equation has the potential to describe an ellipse if it has a solution, if it's not degenerate. But then the question becomes, all right, how do we figure out what the center of this ellipse is, what the foci are, where the vertices are, etc., etc. So let's look at this. So let's look at the process for converting to the standard form of the equation of an ellipse. And we're going to go ahead and use the example that we had last time in order to explain what's going on. So we get 9x squared plus 2y squared plus 36x minus 12y minus 18 equals 0. Now, remember that the goal is to get something of the form x minus h squared over a squared plus y minus k squared over b squared equals 1. Or perhaps the a and the b switched in this notation. But this is what we're going for. So we're going to do some manipulation of this. First of all, we're going to bring the 18 to the other side. We want all the constants there. And we're going to group up all of the x terms together and the y terms together. So we'll look at 9x squared plus 36x and 2y squared minus 12y equals 18. So this is the first step, arranging things with the x's grouped up, the y's grouped up, and the constants on the other side. So step 1, rearrange. Step 2 is going to be to factor out the greatest common factor from each group on the left. So the 9x squared plus 36x, I should say greatest common factor constant, the greatest common constant factor. So we have 9x squared plus 36. Sorry, I misspoke. I should be more precise. In this case, it's the greatest common factor, but in general, it might not be. We want to factor out the coefficient of x squared from the x group and the coefficient of the y squared from the y group. The point is that at this step we want to factor out what we have to in order to get the coefficients of the x squareds and the y squareds to be 1. So we will factor out 9 from this first group to get 9 times x squared plus 4x, and we will factor 2 out from the y group to get 2 times y squared minus 6y, and leave the 18 the same on the right. Step 3, we're going to complete the square in each group, balancing the new terms on the right-hand side. So let's see what that looks like. We're going to try to turn this x squared minus 4x term into something that looks like x minus h squared. And so we're going to say, all right, well, what do we need to add to x squared plus 4x in order to get it to be a perfect square trinomial? And we always look at this number here. We cut it in half and we square it. So we're going to be adding 4 over 2 squared. And similarly, with the second term, y squared minus 6y, we're going to be adding the number negative 6 over 2 squared. Now let me move these, because we're going to need a little more space. So what that means is that we're going to wind up adding 4 divided by 2 is 2, squaring that is 4. We're going to be adding 4 to this x term over on the left, and we're going to be adding 9 to this y term on the left-hand side of the equation. Now, of course, we can't just add in numbers whenever we want. We have to balance that out. So we also need to add something on the right. But the thing to note is that, for instance, this 4 that we've added inside the x group is also being multiplied by the 9 on the outside. So we haven't just added 4 to the left-hand side, we've added 4 times 9. So we actually have to add 18 plus 4 times 9 in order to balance out the adjustment we've made inside the x group, and plus 9 times 2 for the group on the for the y terms, because we've added a 9 inside, but that 9 is inside parentheses that have a 2 on the outside. So we've added not just 9 on the left-hand side, but 18, 2 times 9. So we do need to balance those out, but as long as we do balance out the numbers that we've added inside with values on the right, then we have done things correctly and we can continue the process. All right, so that's step 3. And let's see what happens when we simplify this. We get 9 times x squared plus 4x plus 4 plus 2 times y squared minus 6y plus 9 equals, now 18 plus 4 times 9 is 36, plus 9 times 2 is 18, all works out to be 72. Now, because we completed the square, we can factor each group. And in fact, if we've done it correctly, we're guaranteed that each of these groups factors as a perfect square, and they do. So x squared plus 4x plus 4 is the same as x plus 2 squared. Y squared minus 6y plus 9 is the same as y minus 3 squared equals 72, and we're almost there. We've got the x plus or minus something squared term. We've got the y plus or minus something squared term. The only thing we have left to fix is that we need 1 on the right-hand side. So the last step is to divide both sides by 72. And when we do that and cancel, we get x plus 2 squared over 8 plus y minus 3 squared over 36 equals 1. And now we do, in fact, have the equation of an ellipse in standard form. So we can read some things off of this immediately. We can read that the center of the ellipse is at the point -2, 3. We can see that it's oriented vertically because the denominator of the y term is larger. We have that the semi-major axis, A, is the square root of 36, which is 6. B will be the square root of 8, which is 2 times the square root of 2. And then C will be the square root of a squared minus b squared, which would be the square root of 28 in this case, which is 4 times the square root of 7, or 2 times the square root of 7, I should say. And so from there we can graph out the ellipse and get what we need there. So this is how we can take an equation in just a general form and convert it into the standard form for an ellipse and read off all the information from here exactly the same way as we looked at earlier. All right, there are only 2 more topics that we want to mention briefly. The first is eccentricity. As the foci of an ellipse get further apart or closer together, the ellipse changes its shape. So for a fixed value of A, if we change the where the foci are, then we get different shapes. So for instance, if we put our points here at A0 and negative A0, and then we put our foci very, very close to that point. So if C and A are very close together, then what's going to happen is that the ellipse is going to be very, very thin. Like this. It's going to be stretched out, and the semi-minor axis is going to be much, much smaller than the semi-major axis here. On the other hand, if we take our foci very close to one another, close to the center, like this, then our our ellipse will be much closer to a circle, in fact. We don't often talk about ellipses where the two foci are the same number, but we can. In fact, an ellipse where C is equal to 0, where the two foci are exactly the same point, the center, that's just a circle. And so what happens is that as you move the foci, for a fixed A, as you move the foci further apart, the ellipse gets narrower and narrower. As you bring them closer together, it expands more and more to the shape of a circle. We have a number that we sometimes use to describe how close to a circle an ellipse is. So that definition is the following. The eccentricity E of an ellipse is E equals C divided by A. So, in particular, we can see from here that the eccentricity is always greater than or equal to 0 and strictly less than 1 because we didn't allow C and A to actually be equal to each other. If the eccentricity is equal to 0, then the ellipse is a circle. And if the eccentricity is close to 1, the ellipse is very thin, as in the left-hand side up here. So here we have on the left a large eccentricity E. On the right we have a small eccentricity E. And these can be used in various contexts to describe, okay, we've got an ellipse, but all right, how circle-like is it? Some ellipses are very close to circles. For instance, the orbits of the planets in the solar system are approximately ellipses, or very, very close to being ellipses, with the sun as one of their foci. But the orbits of the planets tend to have pretty small eccentricities, especially the planets like Earth and Mars. Mercury has a slightly higher eccentricity, but most of the planets have orbits with eccentricities very close to 0. On the other hand, most comets in the solar system have a very high eccentricity, an eccentricity very close to 1. They come down and orbit very close to the sun. They also have the sun as a focus of their orbit, but then go way, way off into space before coming back down. So one way of thinking about eccentricity is that for large eccentricity, there's a big difference between your closest and furthest points from a given focus, whereas for small eccentricity, you're always, if you're on the ellipse, approximately the same distance away from a given focus. So the eccentricity gives us a measure of this, but if we have C and A, we can easily compute it, but because it doesn't carry any additional information, then the numbers C and A, we don't usually refer to it when graphing an ellipse. All right, the last point that I want to talk about is an interesting property of ellipses that have to do with the reflection, similarly to how parabolas did. If I have an ellipse and it's got its two foci, and I don't want to make super extreme eccentricity here, one way or the other. So if we've got an ellipse like this, say, clean that up. Oh, sorry. Then we can talk about reflections of things that happen inside this ellipse, similarly to how we did with the parabola. And if some signal comes in and reflects off of the parabola, then again we have the same principle from physics that the angle that the signal comes in and the angle that the signal comes out are going to be the same. Now with the ellipse, there's no sort of outside. It's not like the parabola where there was a direction that things were opening up. But what is interesting is that if you take a point on the ellipse, or go from the focus out to a point on the ellipse and look at the reflection, turns out the reflection is always going to take you exactly to the other focus. No matter where you go and reflect it off, it's going to get to the other. Focus. There are actually quite a lot of applications to this, but perhaps one of the most striking is that if you go to certain buildings, especially quite old buildings, cathedrals and things like this, they will sometimes have these oval-shaped rooms. And what will happen is that they were specifically designed with these two foci in mind. And there will be 2 points in the room where if one person stands at one focus and one person stands at the other, even if the room is crowded and there's lots of noise going on, the person at one focus can even talk normally or maybe even whisper, and the person at the other focus will be able to hear them. Because while the signal coming from the first focus is not very loud and wouldn't be able to punch straight through, it goes out, gets reflected across all of the surfaces of this oval-shaped room, and all combine down again to the other focus at the other end of the room. It's quite a striking phenomenon and one of the most fun applications of the theory of ellipses. It also has many practical applications as well. The book describes how this can be used to eliminate kidney stones in using certain techniques of setting the kidney stone at one focus and a pulsing object at the other that creates vibrations that focus down at the kidney stones and manage to collapse them. We have similar interesting reflective properties with the ellipse as we do with the parabola.